A current of 10 ampere flows in a ring of radius 15 centimeter made of very thin wire. The tensile strength of the wire is equal to 1.5 Newton. The ring is placed in a magnetic field which is perpendicular to the plane of the ring, so that forces tend to break the string. Find B at which the ring is broken. That means maximum tensile strength is given, so you should not produce more than this tension. The ring will break. Okay, if a ring is placed like this, and if the magnetic field is like this, then how will be that force due to magnetic field trying to break the ring? Now, suppose you take a part of the wire, say a part of the wire here. So like this, suppose the current is in this direction, then you have to hold the forefinger into the board. So this is forefinger which represents magnetic field like this, and the current in this direction. That means the direction of current middle finger. Then the thumb will represent a force like this. That means there is a force like this. And it will try to move the string upwards. But the similar part of the wire, coil here, will have a current in this direction. So that will experience a force like this. Similarly, this part of this ring will experience a force like this. And here it will experience a force like this. So here like this, like this. So totally the whole circular ring will be under a tension which is stretching it outside. So every part of the wire will be experiencing a stretching force. So that if that force is very large, that may break the string also. So they are asking you how much maximum magnetic field can be applied so that the ring is just broken. That's what they are asking. So now if you want to solve this problem, and if you want to get the answer for that tension which is developed within the string, let us take the coil like this, circular coil, and we will place it in an x and y axis, and I will take only one part of the coil. I'm very struggling to get a circle. Okay, that's a worst circle. Okay. This is okay. Yes. That's the worst y-axis. I'll take the vertical like this. Yes. Now I'll take a small part of the string here. Here. So each part of the string will be experiencing a stretching force because the whole ring is stretched outside or inside. So there will be a tensile force on each part of the wire. Now, if I take a small part of the wire here, and if I join the ends of that small part, what I have taken here, and let it make an angle, describe an angle d theta here, total d theta. Then, you know, the half angle is d theta by 2. Now, this part of the wire will be, since the whole wire is stretched outside here, 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 everywhere like this. So this part of the wire will be experiencing a stretching force. And I will represent that stretching force as this one. This tension inside the wire. This is the tension inside the wire. Remember, even if the whole ring is stretched like this outside, within the ring, the stretching force is like this, over the length of the ring. So that tension I have represented like this. The whole ring is pulled outside throughout its body. So there will be a stretching force inside the string, and that is represented by this T here. Now, if I draw a horizontal here, like this, and this should be a very small part of the ring actually. So if I draw a horizontal like this here, and like this way here, I think I must have drawn a smaller part of the wire. It's very large actually, it should be very small. Okay, I'll redraw it. I'll take a small piece of the whole wire. rub this. So I'll take only this part of the wire. Then join the ends. This is d theta. Now, if I continue this as a straight line, like this here, and this as a straight line, then this is the tension which is stretching the force, stretching the whole wire outside. This is T and this is T. And if I draw a horizontal here, and then I can find out another d theta here, or d theta by 2. Now, this this y-axis, or this vertical line, and this vertical line, I'll change the color, this one, and this line, they are making an angle d theta by 2, sorry. This is the d theta, and these two lines which I have marked are making an angle d theta by 2. Now draw perpendicular lines to these two marked lines. The perpendicular line to this one is this line, because it is a tangent to the radial part. This is the radius of the circular ring, and this is perpendicular. Okay. What about this horizontal run? That is perpendicular to this y-axis line, like this one. So this is perpendicular to this line, whereas this is perpendicular to this line. So they should also make the same angle made by these two marked lines, that is d theta by 2. So similarly, symmetrical angle will be found here, d theta by 2. Hope you have understood. So this line, radial vector, is perpendicular to tangent here, and this y-axis is perpendicular to this horizontal line. So angle made by these two lines, this one and this one, and angle made by the two perpendicular lines, this one and this one, should be same. Then now tension can be split into two parts. Here, T cos d theta by 2, and tension along this direction is T sin d theta by 2. And what about this tension here? Here also you can have T cos d theta by 2, and here T sin d theta by 2. So I can split this tension as T cos d theta by 2, T sin d theta by 2. This tension as T cos d theta by 2 and T sin d theta by 2. Now these two tensions will act in the same direction. They will add up. 2T sin d theta by 2. What about this one? They will cancel each other. And now this force, the force due to magnetic field, suppose the current due to the current passing to the wire is like this, and if the force due to magnetic field on the loop is like this, force due to magnetic field, if the wire shouldn't break, means this should balance each other. That means force due to magnetic field, which will stretch the wire outside, must be balanced by 2 times T sin d theta by 2. These two forces will cancel themselves, and if the wire shouldn't expand and shouldn't contract, means force due to magnetic field on a current carrying coil or current carrying wire should be balanced by the y component of the tensions, 2T sin d theta by 2. So what is the force on this wire now? Now, if you want to, what is the length of the wire, that piece we have considered, this piece of the wire, its length is, so from here to here, you can have r d theta. So length of the wire is r d theta. Now I have to consider full angle, r d theta. So, so if you want to write the force, I into L cross B, ILB sin theta, sin alpha, something like, I like that icon, right? So F is, vector F is I into L cross B. Now magnetic field is existing perpendicular to the plane of the paper. So sin alpha is 90, that we know. So ILB only. So what is ILB? I is I, L is r d theta. The sample wire that I have taken only from here to here, that r d theta. IL, B, that is what you are going to find out. Sine 90, because magnetic field is outside the plane or inside the plane, it is perpendicular to the plane of the figure, is equal to 2 times. And when this theta taken is very small, this d theta is very small, you can write sine d theta by 2 as d theta only. So 2 times t, I can write it as d theta by 2, because sine theta is sine d theta by 2 is almost equal to d theta by 2 when d theta is very small. 2 gets cancelled. D theta also gets cancelled. What remains is, we want only that B is equal to T divided by IR. That's the only thing which remains here. T divided by IR, and tension, maximum tension that you can apply on the string is given 1.5 Newton. And I that you are passing is 10 amperes, and this is 15 centimeters. 10 amperes, and this is 15 into 10 to the power minus 2. What is B is equal to? This is 10 times. 10 into 10 is 100. 100 into 10 to the minus 2 is 1. So this is 1 Tesla. That is the answer. Thank you.